Every year, over 1 billion pounds of spray foam insulation are used worldwide. This isn't just a number, it's a whole army of invisible wall shields that protect homes from cold, heat, and moisture. But how exactly is a material that expands tens of times in volume and turns walls into a monolithic cocoon born from ordinary barrels of unimpressive liquids? The secret is hidden in two hot hoses, a pressure of over 1,000 pounds per square inch, and an instantaneous chemical reaction. And then the real magic begins, which we will reveal by the end of this video. A special truck or a large trailer pulls up to the house. It's like a mobile factory on wheels. Inside, there are two large barrels, usually 55 gallons each, and a whole system of pumps, compressors, and heaters. From this truck, two long, thick hoses extend directly into the house. The whole secret lies in these two barrels. This isn't finished foam. These are two separate components that, on their own, are rather unimpressive liquids. Technicians call them Component A and Component B. Let's break down what these liquids are. Component A, often called isocyanate, is, you could say, the activator, or hardener. It's a highly reactive substance waiting for its moment to start the process. Component B is a much more complex cocktail. It contains a polyol resin, which is the basis of the future plastic, as well as a whole set of auxiliary substances. Here there are catalysts, which act like a match that ignites the reaction, forcing it to proceed incredibly quickly. Here there is a blowing agent, a special substance that instantly turns into a gas when heated, creating billions of tiny bubbles that form the structure of the foam. Flame retardants are also added here, compounds that make the final product fire resistant. Essentially, Component B is the body and soul of the future foam, and Component A is the key that triggers its transformation. Now let's follow the path of these two liquids. The pumps in the truck start working, pumping Component A and Component B through separate hoses. But here's an important detail. The hoses are heated. A special system maintains the temperature of the liquids in a very narrow range, usually around 130 degrees Fahrenheit. This is critically important because the right temperature ensures the ideal viscosity and guarantees that the chemical reaction will proceed exactly as it should. These two hot hoses run to the hands of the technician, where they are connected to a special spray gun. This gun is not just a sprayer, it's a high-precision mixing device. Until the very last moment, down to the microscopic chamber in the nozzle of the gun, the two liquids never meet. They flow through parallel channels. And now comes the moment of truth. The technician, dressed in a protective suit resembling a spacesuit and a respirator, approaches an open wall with wooden studs. He pulls the trigger. At that very instant, the two streams of hot liquids, under enormous pressure of about 1,000 pounds per square inch, burst into the mixing chamber in the gun's nozzle. They collide with each other, mixing instantly. And immediately, flying out of the nozzle, this mixture hits the surface of the wall. And here, the real miracle begins. What was a liquid mist begins to grow before your eyes. It's like baking bread, but in fast-forward mode, 100 times over. In a matter of seconds, a thin layer of liquid expands, increasing in volume by 30, 60, and sometimes even 100 times. The foam grows, filling absolutely all voids, all gaps and cracks around pipes, wires, and wooden beams. It's like a living organism, swelling and rising, creating a continuous, seamless layer. This chemical reaction is exothermic, meaning it releases a lot of heat. If you hold your hand near the fresh foam, you can feel intense heat. Sometimes, a light steam even rises from it. But here, the story splits, because there are two main types of this foam, and they are very different in their properties. The first type is called open cell foam. During its expansion, the gas bubbles that form inside burst, creating a structure similar to a sponge. If you look at it under a microscope, you can see a network of interconnected pores. This foam turns out to be very light, soft, and elastic. To the touch, it somewhat resembles dense foam rubber. When it fully expands and cures, its excess, which protrudes beyond the studs, is easily trimmed off with a long knife or a special saw, leaving a perfectly flat surface. Open cell foam is an excellent sound insulator. Its spongy structure perfectly dampens sound waves. It is also an excellent thermal insulator, but it allows water vapor to pass through, meaning it breathes, which can be both an advantage and a disadvantage depending on the climate and wall construction. The second type is closed cell foam. This is a completely different beast. During its reaction, the gas bubbles that form do not burst but remain intact, creating a structure of billions of tiny, isolated plastic spheres filled with gas. The result is a much denser, harder, and stronger material. When closed cell foam cures, it becomes so hard that you can walk on it. It doesn't just fill space, it literally glues the entire wall structure together, adding significant rigidity and strength. Unlike its open sister, it is completely impermeable to both air and water. It acts as a vapor barrier, making it the ideal choice for foundations, basements, and in places where maximum moisture protection is needed. Its thermal insulation properties per inch of thickness are significantly higher than those of open cell foam, as the gas trapped in the cells is a better insulator than air. After application and curing, it is also trimmed, but this requires a more powerful tool, as it is much harder. So, at the end of the day, when the technicians roll up their hoses and leave, what remains in place of empty walls is something incredible. Not just a collection of individual pieces of insulation, but a continuous monolithic cocoon, perfectly fitted to every detail of the structure. This cocoon has no seams, joints, or gaps through which cold wind could penetrate in winter or hot air in summer. It has transformed a conventional frame wall into a high-tech thermal envelope. This entire process, from 2 barrels of liquid in a truck to a finished, solid, and incredibly effective insulation layer, takes only a few hours. And that's the whole point and beauty of this technology. It doesn't bring a finished product. It creates it on site, perfectly adapting it to the shape and needs of a specific house. This is the pinnacle of a customized approach in construction, where chemistry serves comfort and energy efficiency. The spray foam insulation market in the United States is a huge, multi-billion-dollar industry. Annually, millions, if not billions, of pounds of these chemical components are poured into the walls, roofs, and foundations of American homes. Experts predict that it will grow by 6% annually, which means that more and more people are choosing this method to insulate their homes. This growth is fueled not by advertising, but by real benefits that you can literally feel and count.
Without nickel, Tesla's electric vehicles wouldn't exist. Every year, over 3 million tons of this silvery metal get extracted from Earth's crust, 70% destined for stainless steel, 30% powering the battery revolution transforming transportation. Picture this. Inside every electric car battery, nickel accounts for up to 80% of cathode weight, storing the electrical energy making 500-mile ranges possible. How does rock buried 2 miles underground become the metal enabling carbon-free futures? How do ancient asteroid impacts create deposits worth billions? Stick around till the end. You'll discover why this metal, discovered in 1751, became overnight the most critical resource for climate solutions, and the shocking environmental price we pay for every kilowatt-hour stored. The story begins in Sudbury, Canada, ground zero for one of Earth's largest meteorite impacts. 2 billion years ago, a 6-mile-wide asteroid slammed into primordial crust with force equaling 6 billion Hiroshima bombs. That cataclysmic collision melted rock 60 miles deep, concentrating nickel-rich magma into deposits mining companies extract today. Standing at crater's edge feels like visiting Earth's wound that never healed. Modern mining descends through vertical shafts, plunging 7,000 feet, deeper than 6 Empire State Buildings stacked vertically. Massive cage elevators, traveling at speeds exceeding 30 miles per hour, drop miners into darkness in under 4 minutes. That's falling through bedrock older than complex life itself. Underground, temperatures reach 120 degrees Fahrenheit from Earth's geothermal heat, requiring industrial air conditioning, pumping cold air through 40-mile tunnel networks. Next comes extraction, where explosive specialists drill blast holes following nickel-bearing veins. Charges containing ammonium nitrate, industrial explosive used in quantities measured by tons, fracture solid rock with controlled violence. The deafening thunder from underground blasts shakes surface buildings miles away, rattling windows in synchronized waves every afternoon at precisely 4 o'clock shift change. Giant load haul dump machines, nicknamed LHDs and standing tall as double-decker buses, scoop 50 tons per bucket. Picture mechanical mastodons navigating tunnels barely wider than their frames. Operating in perpetual darkness, illuminated only by headlamps, drivers maneuver 60-ton machines through labyrinths where wrong turns mean hours backtracking. Every shift, these machines transport 15,000 tons of ore, weight equivalent to 75 blue whales, through underground highways to crushing stations. Surface processing begins where jaw crushers, standing 4 stories tall with opening widths matching garage doors, pulverize boulders into gravel-sized chunks. With bone-rattling vibrations felt through steel-toed boots, hydraulic jaws generate crushing forces exceeding 15,000 pounds per square inch. Operators monitor crack propagation. Rocks splitting wrong create jams requiring dangerous manual intervention with jackhammers. Conveyor systems stretching 8 miles, longer than Central Park, transport crushed ore to grinding mills. Inside rotating drums 30 feet in diameter, 25-ton steel rods tumble with ore, creating grinding cacophony resembling continuous thunder. Processing 12,000 tons hourly, that's loading freight trains non-stop. This powder, finer than beach sand, flows to flotation cells, where chemicals separate nickel sulfides from waste rock using bubble physics. Nickel concentrate emerges containing 20% metal, ready for the real challenge: purification. Next comes roasting, a pyrometallurgical inferno where concentrate gets heated in massive kilns to 1,400 degrees Fahrenheit. At these temperatures, sulfur burns away as sulfur dioxide, leaving behind nickel oxide mixed with iron. Picture industrial-scale barbecuing where the meat is rock and smoke contains compounds requiring scrubbing before atmospheric release. The roasted material, now crumbly and porous like volcanic pumice, moves to smelting furnaces, where temperatures climb to 2,600 degrees Fahrenheit. Electric arc furnaces, consuming power equivalent to small cities, enough electricity to run 12,000 homes, melt oxide into liquid matte. This molten mixture, containing 60% nickel and 40% other metals, glows white-hot like captured starlight. Every 2 hours, furnaces tap this liquid fire into ladles holding 200 tons. The purification process intensifies with converting, where oxygen blasted through molten matte at supersonic speeds burns away remaining sulfur and iron. Massive Peirce-Smith converters, rotating horizontal cylinders 40 feet long, operate like blast furnaces lying sideways. Inside these rotating drums, chemical warfare occurs. Oxygen attacking sulfur bonds, creating temperatures hot enough to vaporize copper. This step is critical because timing determines purity. Blow too long, nickel oxidizes wastefully. Too short, impurities contaminate final product. Operators monitor color changes in flames shooting from converter mouths. Blue flames means sulfur burning, yellow indicates iron removal, clear white signals nickel ready. That visual chemistry, unchanged for centuries, guides decisions affecting millions in product value. After converting, nickel matte achieves 78% purity, but battery manufacturers demand 99.9%. After converting, the real magic begins: electro-refining. Here, physics and chemistry converge in massive electrode halls housing thousands of cells. Impure nickel anodes, cast into plates weighing 300 pounds each, suspend in electrolyte baths containing nickel sulfate and sulfuric acid. Electric current flowing through these baths, think industrial-scale electroplating, dissolves nickel atoms from anodes, transporting them through liquid to deposit on pure nickel starter cathodes. Picture this: over 10 days, nickel migrates atom by atom across 6-inch gaps. Impurities like cobalt, copper, iron stay behind, falling as sludge to cell bottoms. This sludge, later processed separately, contains precious metals including platinum, gold, palladium, making waste worth more than many ores. Temperature control matters critically. Too hot, dendrites form, metal crystals bridging electrodes causing shorts. Too cold, deposition slows uneconomically. Electro-refining requires surgical precision in industrial setting. Computer systems monitor voltage, amperage, temperature across 15,000 individual cells simultaneously. Operators adjust current by milliamps. Modern refineries achieve nickel purity of 99.99%, only one impurity atom per 10,000. That's purity rivaling semiconductor-grade silicon. After 10 days, workers crane lift finished cathodes, now coated with 400-pound nickel deposits from baths. Mechanical strippers peel nickel from starter sheets like removing wallpaper. These pure nickel sheets, called cathodes, get melted into pellets for battery manufacturers, or alloyed with chromium and iron for stainless steel. The energy intensity staggers. Producing 1 ton of battery-grade nickel consumes 50 megawatt-hours, enough electricity to power average American homes for 60 days. This industry transformed radically in 15 years. Back in 2010, nickel prices averaged $7 per pound, used primarily for stainless steel. Battery applications consumed less than 5% of global production. That all changed when Elon Musk's Master Plan 2 announced Tesla's battery gigafactories in 2016. The breakthrough came when battery chemistry shifted from cobalt-heavy NCAs to nickel-rich NCMs, nickel, cobalt, manganese cathodes containing 80% nickel. Suddenly, every electric vehicle needed 110 pounds of nickel. Global demand exploded. Prices spiked to $9 per pound by 2022. Indonesia, containing 21% of world's reserves, transformed from minor player to dominant producer. Today, battery applications consume 43% of new nickel production. By 2035, International Energy Agency projects batteries will consume 75%, driven by 200 million electric vehicles requiring 23 million tons cumulatively. Carbon emissions drop by 18% when recycling nickel versus mining virgin ore, equivalent to removing 3 million cars annually. Industry saves over $22 billion yearly through recycling. Processing costs drop 31% because smelting scrap requires half the energy of complete ore processing. So here's the secret promised. Nickel is humanity's transition metal, literally bridging fossil fuel era to electric future. But here's the dark truth. Extracting nickel for just one EV battery produces 8 tons of CO2 emissions. That electric car carries invisible environmental debt, requiring 35,000 miles of driving before breaking even with efficient gasoline vehicles. The green revolution isn't free. It's an energy trade-off where extraction today enables emission reductions tomorrow. From asteroid impacts to electric highways, cycle completes. We're mining ancient cosmic collisions to power climate solutions. Nickel doesn't solve pollution, it relocates it, concentrates it, transforms it into manageable problem. That's not failure, that's engineering reality. Every solution creates new challenges. The question isn't whether mining nickel harms Earth, it does. The question is whether preventing catastrophic climate change justifies temporary scars.
Imagine a magnet so powerful it can lift a weight 1,000 times its own. How can a piece of metal stop a jet engine turbine or become the heart of a Tesla electric motor? The secret lies in rare earth elements, materials that hide more mysteries than gold or platinum. To create a single neodymium magnet, you have to move mountains of ore, melt metal at over 2,700 degrees, and use technologies that resemble alchemy. But there's a detail that almost no one knows about. Watch till the end, and you'll learn a secret that will change your understanding of the power of metal. The mining and initial processing of rare earth ores are a key stage in the production of neodymium magnets, as this is where the foundations for obtaining the necessary components are laid. This process begins with the large-scale mining of ore, containing the rare earth elements that make up neodymium. In the first stage, the ore is extracted from the earth using various mining methods. This can be either open-pit mining or underground mining, depending on the depth and type of the deposit. After extraction, large chunks of ore are delivered to crushing plants. At the crushing plants, the ore undergoes primary crushing. Large boulders of ore pass through a series of crushers that gradually reduce their size into smaller fractions. This is necessary for further effective processing and extraction of valuable components. The crushed ore may then be fed into mills for further fine grinding into a powder or a pulp, which consists of fine ore particles suspended in water. The next critically important stage is ore enrichment, the purpose of which is to separate the rare earth minerals from the waste rock. This process can involve various methods. One of the most common methods involves mixing the crushed ore with water and special reagents. These reagents selectively attach to the surface of the rare earth minerals, making them water repellent. Air is bubbled through the mixture, creating bubbles to which the hydrophobic minerals adhere and rise to the surface, forming a froth that is then collected. Heavier particles settle faster, allowing them to be separated from the lighter ones. Some rare earth minerals have magnetic properties, which allows them to be separated from non-magnetic components using magnetic separators. After enrichment, a concentrate is obtained, which contains a much higher concentration of rare earth elements. However, this concentrate is still not a pure metal. It requires further chemical processing, which usually includes dissolving the valuable components with acids or alkalis, precipitation, solvent extraction, and ion exchange chromatography. These processes allow for the separation of each rare earth element individually and its purification to a high degree. For example, neodymium is separated from other rare earth elements like praseodymium or samarium. The final result of this complex chain of processes is the production of high-purity neodymium oxide, which is then reduced to metallic neodymium. This metallic neodymium, in the form of granules or ingots, is ready for the next stage, alloying with other components to create powerful neodymium magnets. The entire process requires strict quality control and significant energy expenditure, but is absolutely necessary to obtain the raw material for the production of these strategically important materials. After the careful extraction and purification of rare earth elements, particularly neodymium, comes one of the most crucial stages in the production of high-performance neodymium magnets: alloying. This process demands extreme precision and control, as the final microstructure and, consequently, the magnetic properties of the finished material depend on it. The purified metals, neodymium, iron, and boron, are carefully weighed in strict proportions. These three elements are the main components of the alloy, providing its unique magnetic characteristics. In addition to them, small amounts of other elements, such as dysprosium, terbium, cobalt, or copper, may be added to the alloy. These additives are introduced to achieve specific properties, for instance, to increase the magnet's temperature stability, improve its resistance to demagnetization, or modify the material's brittleness. The exact composition of the alloy is a trade secret for many manufacturers and varies depending on the desired final characteristics of the magnet. The weighed components are placed in a specialized vacuum induction furnace. The use of a vacuum is critically important as it prevents the oxidation of the rare earth metals and other components at high temperatures. Oxidation would lead to the formation of undesirable phases, which would degrade the magnetic properties of the material. Induction heating ensures rapid and uniform melting of all components, creating a homogeneous melt. The melting temperature in such a furnace can reach over 2,700 degrees Fahrenheit. After achieving a complete melt and homogenization of the alloy, the stage of rapid cooling, known as the strip casting method, begins. This is a key moment for forming the optimal microstructure. The molten metal is poured in a thin stream onto a rapidly rotating, cooled drum. Contact with the cold surface of the drum leads to an extremely rapid cooling of the melt at a rate of up to millions of degrees per second. This extremely rapid cooling prevents the formation of large crystal grains and allows for the formation of an amorphous or microcrystalline structure. Instead of the typical crystalline structures formed during slow cooling, extremely fine grains are formed. This process is also known as rapid solidification, and it is fundamental to achieving high magnetic properties. The resulting material takes the form of thin, easily crumbled flakes or ribbons. This unique microstructure, with very fine, often anisotropic grains, is the key to the high strength of neodymium magnets. The smaller the grain size, the more difficult it is for the magnetic domains to change their orientation, which provides high resistance to external demagnetizing fields. Thus, the alloying and rapid cooling stage is fundamental for forming the magnetic characteristics that will later be locked in during subsequent production stages. After the alloying and rapid cooling stage, when thin flakes or ribbons of the neodymium iron-boron alloy have been formed, a stage called hydrogen decrepitation begins. Every year, the world cranks out over 100 million cubic meters of medium-density fiberboard. That's such a massive amount that you could build a road around the entire planet with it, every single year. Imagine this. What was once trash, sawdust, wood chips, and scrap paper, is now transformed into a material worth over $25 billion. China controls half of the entire volume, while Europe and the US add millions of cubic meters each year. But what's really going on behind the factory walls, where wood dust goes from being waste to perfectly smooth panels? If you stick around to the end, you'll learn a secret that's usually kept hidden. The foundation for medium-density fiberboard isn't whole logs, but what used to be considered rubbish: sawdust, wood chips, offcuts, and even old scrap paper. It's a triumph of smart resource use. These mountains of wood waste are brought to the plant and first get a thorough cleaning. Powerful magnets pull out any metal contaminants, nails, staples, while screening systems remove sand and stones that could damage the expensive equipment. After that, the raw material goes into a huge vat where it's washed and steamed with hot steam. This isn't for cleanliness. It's done to soften the lignin, the natural glue that holds the wood fibers together. Now comes the most important step, the one that separates medium-density fiberboard from its rougher cousin, particle board. The prepared, softened wood chips are fed into a machine called a defibrator, or refiner. Imagine two giant metal plates, like millstones, spinning towards each other at enormous speed. On their surfaces is a complex pattern of sharp ridges and grooves. The wood mass gets caught between these discs, and they literally comb it apart into its tiniest components, tearing it into individual wood fibers. This isn't shavings anymore. It's something like a fluffy, moist cotton or wood flour. We've just deconstructed the wood down to its basic building blocks. Next, this fibrous mass needs to be dried. But it has to be done very quickly before the fibers start to stick together. So they're blown into a long, hot tube dryer. A stream of hot air picks up the fibers, and as they fly through this tube, all the excess moisture evaporates from them, And right here, while the fibers are still hot and flying in this whirlwind, the next key stage happens: resonation. A fine mist of a binding agent is sprayed into the airstream through special nozzles. This is urea resin, our glue. This mist envelops every tiny fiber, coating it with a thin, sticky film. It's a very efficient method that guarantees a perfectly even distribution of the glue. Now this resin-soaked, dry, and light as fluff mass is ready to become a board. It goes into a forming machine. The stream of fibers settles onto a wide, moving conveyor, forming a thick, fluffy, and perfectly uniform mat. Special rollers slightly compact it, and giant knives cut off pieces of the required length. It's already starting to look like a future board, but for now, it's just a thick, soft mattress of wood fluff. And now comes the climax: hot pressing. This fluffy mat rolls into a giant press. This can be either a multi-opening press that squeezes a whole stack of boards at once, or a continuous press that looks like giant moving tracks. And here, our mat is hit by two powerful forces at the same time. First, colossal pressure. The press plates squeeze our fluffy mattress with hundreds of tons of force, reducing its thickness several times and squeezing out all the air. The wood fibers are pressed tightly against each other, forming an incredibly dense structure. Second, a high temperature of 400 degrees Fahrenheit. That's 200 Celsius. This heat does two things. It activates the resin, causing it to polymerize and permanently glue the fibers into a single solid block. And at the same time, it evaporates any remaining moisture, which escapes from the board as hissing steam. After a few minutes in this steel embrace, the fluffy mat transforms into a hard, dense, perfectly flat, and still very hot board of medium density fiberboard. After the press, the hot boards can't just be stacked. They need to be cooled to relieve internal stresses. They're placed in a special fan cooler, which looks like a giant filing cabinet, where they slowly cool while being fanned with air. Once the boards have cooled, it's time to give them a finished look. First, they're stacked in high piles and left to rest for a few days. This stabilizes their internal structure. Then, each board goes through a sanding machine. Imagine a giant belt sander with several heads. Wide abrasive belts remove a thin surface layer from both sides, bringing the board to a perfectly precise thickness, for example, 16 or 18 millimeters, and creating that famous smooth as paper surface. And the final touch, cutting. Huge saws cut the large industrial boards into standard commercial formats. After this, each batch goes through strict quality control. Its density, strength, thickness, and surface quality are checked. The finished, perfectly smooth boards are labeled, packaged, and sent to furniture factories, where they will become the foundation for elegant and stylish items in our homes, silently demonstrating the noble path that ordinary wood dust can travel. The global market for medium-density fiberboard is a giant machine that turns over more than $25 billion a year. And this machine has no plans of stopping. Forecasts say it will grow by 6% every year. That means the demand for this smooth material is just insane. So who's the head chef in this kitchen? The undisputed king is China. It produces over 50% of all the medium-density fiberboard in the world. But Europe is no slouch either, with powerful players like Germany, Poland, and Turkey producing millions of cubic meters of high-quality board. Now for the volume. Every year, about 100 million cubic meters of medium-density fiberboard are produced worldwide. That number is so huge, it's impossible to imagine. Let's try. Picture a road. If you took all that medium-density fiberboard and built a road 10 meters wide and 25 centimeters thick, you could wrap that road around our entire planet at the equator every single year. It's an endless stream of material being turned into furniture, doors, and panels for our homes. Every year, the world melts over 1 billion tons of pig iron. But where does all that fiery metal come from? Imagine a giant furnace as tall as a 35-story skyscraper that never sleeps. Its guts glow like the Earth's core, and the temperature hits 3,600 degrees Fahrenheit. That's 2,000 Celsius. This is a blast furnace. They don't just melt metal here. They give birth to the heart of industry. But there's a secret that only the guys standing at the tap hole know. If you stick around to the end, you'll find out what's really happening in the center of this burning fortress and why it changes everything. Imagine a colossal tower, taller than a 35-story skyscraper. The ground beneath your feet vibrates slightly from its relentless work, and the air is filled with a hum, like the breathing of a giant beast. At night, its top glows, pushing back the darkness. This is a blast furnace, a massive vertical smelter where 24 hours a day, 7 days a week, the magic of turning ore into metal happens non-stop. Why blast furnace? The name comes from the process itself, and it's no accident. The whole secret to a blast furnace is the constant blast of incredibly hot air that fuels the fire and kicks off all the necessary reactions. If you were to slice a blast furnace open, you'd see it looks like a stretched out bottle. Every part of it has a name and a purpose. The walls of the furnace are lined with special refractory bricks, capable of withstanding temperatures that would melt solid rock. This is a true fortress, built to tame fire itself. So what do they feed into this fiery throat? The process is like cooking from a very strict recipe. The mix of ingredients loaded into the furnace is called the charge. Here are its main components: iron ore, fuel, coke, and fluxes. These three ingredients are loaded into the furnace in precisely measured layers. A layer of coke, then a layer of ore with fluxes, then coke again, and so on. Every few minutes, a new batch weighing tens of tons is sent into the furnace. The iron ore is the foundation of it all. They usually don't just use raw ore dug from the ground, but specially prepared sinter or pellets. These are baked clumps of fine ore, or rolled balls of ore concentrate. The main goal is to have as much iron oxide in the raw material as possible, from which the oxygen will later be ripped out. Coke is coal that's been cooked in special ovens without access to air. After this treatment, it becomes strong, porous, and burns with an immense amount of heat. But that's not its only role. The carbon that makes up coke is the real magician that turns ore into metal. The flux is most often ordinary limestone. Why is it needed? The ore and coke always have useless impurities, so-called gangue. The limestone helps to bind these impurities, forming an easily meltable slag. So, the charge is loaded. What's next? This is where it gets interesting. Two streams move towards each other. From the top, the layers of the charge slowly descend, and from the bottom, a hurricane of superheated gases rushes up to meet them. It all starts at the bottom, in the hearth. Through special pipes called tuyères, air heated to a scorching 2,200 degrees. Fahrenheit, 1 to 200 Celsius, is blasted into the furnace under huge pressure. That's hotter than volcanic lava. Meeting the red-hot coke, the oxygen in the air instantly ignites. The temperature in this zone skyrockets to 3,600 degrees Fahrenheit, 2,000 Celsius. This creates carbon dioxide. But as it rises higher and passes through new layers of coke, it turns into another gas, carbon monoxide. And this gas is the real oxygen thief. As this searing hot stream of gas rises up the furnace shaft, it envelops the chunks of ore and begins to greedily rip the oxygen from them, leaving behind reduced, spongy iron. The reduced iron continues its journey downward into hotter and hotter zones. It passes through the glowing layers of coke and, like a sponge, begins to soak up its carbon. And here's where something amazing happens. Pure iron melts at a very high temperature of 2,800 calories, 1,530 nanometers. But soaking up carbon dramatically lowers that melting point. That's why a blast furnace doesn't produce pure iron, but an alloy of iron and carbon, pig iron, which becomes liquid at just 2,200 nanometers, 1,200 nanometers. Roughly every 40 to 60 minutes, enough liquid products have collected in the bottom of the furnace. It's time for the climax, a truly mesmerizing sight. A furnace worker, the keeper, uses a special drill to punch open a hole in the furnace wall, the tap hole. First, they tap the slag. It's lighter than the iron, so it floats on top. It's a molten, lava-like mass that flows into special ladles. And then they open the iron tap hole, and a dazzling, sparking stream of molten metal erupts with a roar. This is the river of fire. The temperature of this stream is around 2,700 degrees Fahrenheit, 1,500 Celsius. It flows down special troughs, bathing everything around in a blinding light, and fills giant ladles that look like railway tankers. Each of these ladles holds hundreds of tons of liquid metal. From here, the pig iron will be sent to its next stage, either poured into molds, or, more often, sent for further processing into steel. A blast furnace is an amazing operation that produces more than just pig iron. The byproducts are just as important. The blast furnace slag, which we've already mentioned, becomes a valuable raw material for making cement, building blocks, and road aggregate after it's cooled and crushed. The blast furnace gas that comes out of the furnace isn't just released into the atmosphere. It's cleaned of dust and used as fuel to heat the very same air that's blasted back into the furnace. It's a closed-loop system that makes the process more economical. Without a doubt, metallurgy is a serious challenge for the environment. However, modern technologies are constantly evolving. When blast furnaces are modernized, powerful filters and cleaning systems are installed to capture dust and harmful gases. Scientists and engineers around the world are working on creating green technologies, like using hydrogen instead of coke, to make metal production cleaner. But for now, the blast furnace remains the king of metallurgy. And every time you see a bridge, a skyscraper, or a train, remember these fiery giants and the people who tame rivers of fire to give the world a strong and reliable foundation. For 75 years, from the late 19th century to the 1970s, the USA was the undisputed world leader in the production of pig iron, steel, and rolled products. During this period, the American iron and steel industry wasn't just a sector of the economy, it was the key, or barometer, of the American economy. In the 1920s, for example, the country produced about half of the world's pig iron. Imagine that. Every other ton of this strategic metal in the world was born right here in American furnaces. Every year, the world produces over 130 million tons of glass. But few people know that behind every clear window, bottle, or skyscraper facade lies a true symphony of fire, air, and light. Imagine a river of molten sand flowing over a mirror of tin, giving birth to perfectly flat sheets of glass so smooth they can reflect the clouds. But there's another kind of glass, one that's alive, with a soul, created by the breath of a craftsman and the fire of a furnace. Stick around to the end, and you'll see how ordinary sand travels through a 3,000-degree journey to become the transparent marvel our world is made of. While the vast majority of architectural glass today is born from a perfectly flat, fiery river flowing over molten tin in the float process, the true soul of the material is revealed in the methods that give it character and uniqueness. This journey from a simple, transparent sheet to a work of decorative art is a fascinating one. To create glass with individuality that carries the mark of a human touch, craftsmen still turn to techniques that have existed for centuries. A glassblower dips his long, hollow pipe into a furnace where a mass of sand and other minerals boils at 2,000 degrees Fahrenheit. He gathers a honey-like ball of glowing glass on the end of the pipe and, skillfully rotating it, begins to blow air into it. The initial bubble, born from his breath, gradually transforms into an elongated, shining hollow cylinder. Thanks to the force of gravity and skillful swinging, this cylinder can reach several feet in length. After the ends of the cylinder are cut off, it's sliced lengthwise and placed back in the furnace. There, under the heat, it slowly unrolls like a scroll, and the craftsmen smooth it into a flat sheet. Glass born this way is never perfectly flat. It's alive, retaining subtle waves, tiny air bubbles, and fine lines that tell the story of its fiery birth. This glass has a watery, organic quality that can't be replicated by a machine. But the creation of unique glass doesn't stop at forming the sheet itself. Other methods transform ordinary sheets into complex decorative elements. Fusing allows artists to literally paint with glass. Different colored pieces of glass are arranged on a base sheet and sent into a kiln, where at 1500 degrees Fahrenheit, they melt together into a single piece, creating bright, painting-like compositions. Closely related is the process of slumping, or bending, where a flat sheet of glass is heated until it becomes soft and sags under its own weight, taking the shape of a ceramic or metal mold placed beneath it. This allows for the creation of curved panels and three-dimensional glass sculptures. Modern technologies add even more possibilities. Lamination allows for baking colored films, fabrics, or even thin sheets of metal between two layers of glass, creating endless variations of color and texture. Sandblasting and chemical etching remove the top layer of glass, making it matte and creating intricate patterns on its surface, from simple geometric shapes to photorealistic images. In this way, by combining ancient crafts with cutting-edge technology, modern production transforms simple glass into an expressive architectural material capable of shaping light, color, and space. In today's world, where tons of used glass containers are collected daily, the journey from the recycling bin to a new bottle isn't just remelting. It's a high-tech odyssey driven by computers and light. Imagine a mountain of crushed glass, dozens of feet high, where clear, green, and brown shards are mixed with labels, caps, and ceramic contaminants. Turning this chaos into pure raw material is a job for a whole complex of smart machines. It all starts with mechanical crushing, where steel hammers turn bottles and jars into fragments a few inches in size. This stream of glass, like a moving river, embarks on a journey through a labyrinth of sorting systems. First, powerful magnetic separators pull out any steel contaminants, and then eddy current systems literally shoot aluminum caps and foil into separate containers. Powerful blasts of air blow away light paper labels and plastic residue. But the hardest task is yet to come. Removing impurities that are almost identical to glass in weight and size, like pieces of ceramic, stone, or porcelain. These enemies of glass don't melt at standard temperatures and turn into defects in new products, so their removal is critically important. This is where optical sorting comes into play. The glass fragments are accelerated on a conveyor belt to high speed and fly through a scanning zone. For a split second, each fragment is illuminated by a bright light, and high-speed cameras take hundreds of pictures. A computer system, with lightning speed, analyzes the images, identifying foreign bodies by their transparency, structure, and shape. As soon as the system spots an opaque piece of ceramic, it instantly calculates its trajectory and commands a battery of air jets. A precise, sniper-like puff of compressed air knocks the unwanted element out of the mainstream, sending it to waste. This process is repeated thousands of times a minute. At the same time, an equally important sorting by color takes place. The same optical systems analyze the spectrum of light passing through each fragment. The machine distinguishes between crystal clear, rich green, and deep brown glass. Depending on the set program, the system can, for example, select only clear glass, knocking out all colored fragments with air jets, or separate the stream into 3 distinct color fractions. The result is a perfectly clean, color-sorted raw material, cull it, ready for a new life without any loss of quality, which is the pinnacle of the modern circular economy. This raw material can then be used to make flat glass. The birth of modern flat glass is a symphony of fire and precision, a spectacular process that turns ordinary raw materials into perfectly transparent sheets. It all begins in a massive melting furnace, the fiery heart of the plant that runs continuously for years. Into this furnace, which resembles a lake of molten fire, a carefully measured mix, or batch, is loaded, consisting of pure quartz sand, soda ash to lower the melting temperature, and limestone for stability. A significant amount of cullet, or crushed recycled glass, is added to this to help speed up the melting process. Inside the furnace, at hellish temperatures approaching 3,000 degrees Fahrenheit, these solid components slowly transform into a uniform, viscous liquid. The melting process is strictly controlled to ensure all particles are completely dissolved and gas bubbles are removed, creating a flawlessly pure melt. From the furnace, this stream of glowing orange molten glass, resembling a river of lava, flows smoothly into a bath of molten tin. This is the culmination of the process known as the float process. The tin bath, stretching for hundreds of feet, has a perfectly smooth, mirror-like surface. Since glass is lighter than tin and doesn't mix with it, it spreads out over the surface, forming a perfectly flat ribbon of uniform thickness. Gravity levels it from the bottom, and surface tension smooths it from the top, creating impeccable optical quality. The speed at which this ribbon is pulled from the bath determines its final thickness with pinpoint accuracy. After forming a perfectly flat surface, the glass ribbon, still very hot but now solid enough to hold its shape, enters the calmest but most critical stage, annealing. It enters a long tunnel known as an annealing layer. If glass is cooled too quickly, its surface will contract faster than its interior, leading to massive internal stresses that will make it brittle and prone to shattering. In the layer, however, the glass temperature is slowly and controllably reduced over several hundred feet, from over 1,000 degrees down to room temperature. This process allows the entire sheet, both surface and core, to cool evenly, relieving all internal stresses. From the other end of the layer emerges a single, flawless, continuous ribbon of perfectly transparent, stress-free glass, ready for automatic cutting into huge sheets that will become the windows, facades, and doors of our world. Imagine this. Every year, the world cranks out over 100 million tons of nuts and bolts, the invisible heroes of our industrial world. They hold together our bridges, our planes, our ships, and even our tallest skyscrapers. But few people know that behind every single one lies a process with precision down to 1,000th of an inch. We're talking metal cleaned in acid, forged under massive presses, hardened at over 2,000 degrees, and tested to its breaking point. So what makes an ordinary bolt strong enough to hold hundreds of tons? Stick around, and you'll learn the secret that turns a simple piece of steel into a part the whole world depends on. A high-volume nut and bolt plant isn't just a factory. It's a high-tech powerhouse where raw steel becomes the hardware that holds our world together. The whole thing is a complex, multi-stage marathon of machining, stamping, heat treating, and non-stop quality control. It all starts with the raw material. High-quality steel wire rod comes in, but it's dirty. First, it needs a serious cleaning to get rid of rust and scale. The most common way to do that? A chemical bath. We're talking a process called acid pickling, where the steel gets a dip in sulfuric or hydrochloric acid. This stuff eats away all the grime, leaving the metal surface perfectly clean and ready for what's next. After the acid bath, the wire is thoroughly rinsed with fresh water to get every last drop of acid off. Then it's dried. For an even deeper clean, some plants use sandblasting or mechanical grinding. You might even see a process called electro-cleaning, which zaps the surface to level it out and boost its rust resistance. On the big production lines, they combine everything: mechanical scrubbing, a chemical dip, a rinse, and a dry. And they don't just eyeball it. Quality control uses visual checks and special instruments to make sure that surface is perfectly clean. Before it moves on, the metal gets a temporary rust preventive coating to keep it pristine during storage and handling. The main ways to make a bolt are cold forming and turning. Cold forming is the real workhorse here. That's where a machine takes the metal wire and shapes it under massive pressure, all without heat. The wire feeds through a series of dies that hammer it into the shape of a bolt. First, the round shank, then the head, usually a hex head so you can get a wrench on it. The beauty of cold forming is that it's incredibly precise, makes the steel stronger, and wastes almost no material. Once the head and body are formed, it's time for the threads. Here, they use a method called thread rolling. Instead of cutting the threads, the bolt blank is forced between special dies that literally press the threads into the metal. This process makes the threads incredibly strong and durable. Some of these high-speed lines can churn out hundreds of bolts a minute. For nuts, they often use hot forging. Steel blanks are heated up to a blistering 2,200 degrees Fahrenheit. That's about 1,200 Celsius, making the metal soft and pliable. Then, a press forges the iconic hex shape. After that, a hole is punched through the middle, and the internal threads are cut on special machines called tappers. Just like bolts, nuts go through heat treatment to make them tough and wear resistant. Heat treating is where a bolt gets its backbone. It's a two-step process, quenching and tempering. First, in quenching, the bolts are heated up and then rapidly cooled. This makes the steel incredibly hard, but also brittle. So the next step is tempering. They're reheated to a lower temperature, which gets rid of the brittleness but keeps all that strength. This is how bolts get their specific grade or property class. After heat treating, every batch goes through brutal quality control. Sample bolts are checked for size, strength, thread accuracy, and any surface defects. We're talking micrometers, go-no-go gauges, and special optical sorters. Any parts that are out of spec are either rejected or sent back for reprocessing. To fight off rust, most bolts and nuts get a protective coating. This could be zinc plating, hot dip galvanizing, or special zinc flake coatings. This is what keeps them from rusting away, especially out in the elements. The finished products are then sorted by size and strength, boxed up, and prepped for shipping. Modern plants have automated lines cranking out hundreds of thousands of these a day. The parts travel on conveyors to automatic sorting machines that use optical sensors to check every last one. Anything that's damaged or not up to snuff gets kicked out. This makes sure only top quality hardware makes it to the packaging line. From there, the nuts and bolts go into automated bagging lines with inline scales and counters that measure out the exact quantity for each package. This could be small plastic bags, cardboard boxes, or bulk bins, depending on what the customer needs. The packages are labeled with all the key info: size, grade, manufacturer, and date. For big industrial orders, they're often packed in bulk bags or large containers to make shipping and storage easier. The whole process is automated to ensure the packaging is sealed tight to keep out moisture, dust, and prevent any damage in transit. Even though most of it is automated, there's still a human touch. For special kits or custom orders, workers will manually check the quality of the packaging, assemble the right mix of nuts and bolts, box them up, and get them ready to ship out. This flexibility allows them to meet specific customer needs with pinpoint accuracy. After packaging, the products go through one last check to make sure the labels are right and the packages are sealed. Then, they're sorted in the warehouse by order and prepped for dispatch. And it's not just standard stuff. Many plants also make custom fasteners based on a customer's specific blueprints, which is crucial for specialized industries like aerospace, automotive, or heavy construction. The global market for fasteners is on a steady climb, and it's all driven by a few key things. First up, construction. As countries spend more on infrastructure, we're talking bridges, roads, and new buildings, the demand for these steel connectors goes through the roof. Second, the automotive and machinery industries. Every car, truck, and piece of factory equipment is held together by hundreds of high-quality fasteners. As those industries grow, so does the need for top-grade nuts and bolts. For example, in Europe, car production is expected to climb, which directly boosts the demand for metal products, including fasteners. At the same time, the steel industry itself is getting smarter, using digital tech and automation to produce better, more specialized products. Of course, the cost of raw materials like iron ore and energy can affect things. But at the end of the day, as long as we're building, driving, and manufacturing, the demand for nuts and bolts isn't going anywhere.